So I have been putting together an order for some antibodies, and really this is the culmination of about 2 weeks worth of work. First, I do the sketches, put everything together with the way that I imagine it, but then I have to assemble the sequences. And this is, I think there's about 85 constructs I'm ordering in this order. So I've got to assemble the DNA sequences exactly for all 85 of them, get them uploaded to the place where we have them synthesized, download them, and check them over, what I call the QC step, to make sure they're exactly, precisely, exquisitely as I designed and expect them to be. So it takes some time.
And when they deliver what you've ordered, what does it look like?
Pretty underwhelming, I would say. It comes in a little plate. This order that I'm putting together today will fill one of these plates, 96 wells. It comes as a little dried up piece of nothing in the bottom of the well that you then have to resolubilize, and that plate alone is going to cost us about 25 grand. So, but that's the underpinnings, the substance, or at least the originating part of what will become the material drug. I've been putting together. I'm coming to the culmination of about 2 weeks worth of work, where we first sketch out a design for an antibody, and ensuring that we have all the component parts that we want and all the mutations that we're looking for. And once we've done what is essentially the sketches of the antibodies, then I have to go through and assemble the nucleotide sequences. And so this is the DNA that will encode the final antibody, and it has to be precisely right. So it takes me, after I do the designs, which takes me a couple of days to get everything exactly as I want it, then I have to come in and actually assemble the DNA sequences in what we say is in silico, or in the computer. That can take a week, although it is a lot of like modular cut and paste, but again, it has to be very precise. Linker lengths, mutations, all these small details become very important, and you can see this is actually a pretty big sequence here. And then what I do is I take this sequence, this digital sequence, I upload that to the commercial entity that does our gene synthesis for us, and they will actually do what they call the oligonucleotide synthesis, which is assembling the GC, GG, CC, GC for 1,464 bases. They assemble that through basically a chemical process. And then at the end of the day, once they've completed, this particular order has about 85 constructs in it, they send us the DNA in a little 96 well plate about yay big with individual wells, and there's just a little bit of dried crunk at the bottom of the well, which is the DNA, but it is exactly conforms to what I ordered, and each one different from the other. And then that is essentially what we solubilize, transfect into cells, and the cells produce the antibody for us. So between starting a design, starting the sketches that I showed you here for design, assembling the sequences, doing the quality control to ensure it's exactly, precisely, exquisitely as designed, sending it off for synthesis, having it synthesized, shipped to the place where that we then solubilize, transfect them into cells, takes about a month and a half. So that's the kind of rhythm that we work with, is from the conception to design to ordering the synthesis to receiving the synthesized DNA plate to transfecting that DNA into cells, expressing and purifying the antibody that we then set out to characterize and determine the properties of. If I designed it well, it's stable. That's the thing. The stability of the molecule is encoded in this sequence. It has nothing to do whether I drop the plate. Well, if you mix it up with the other DNA, it has to be pure DNA. So the stability is really encoded in this sequence. If there's things that proteins don't like and that I've done in the sequence, But this is what we do essentially. We're protein engineers and have ways of iteratively designing something that's not too far off of something we know. So we know that it's stable, and then we determine the properties of it. Once we get it, so we get this plate of DNA, we solubilize it, we can amplify that DNA in bacteria and then purify it. And once we have enough purified DNA, we transfect it into cells, which is really just a fancy way of saying we chemically insert the DNA inside the cell where it has access to all the protein translational expression machinery that will then express what is encoded in that DNA and secrete it outside of the cell where we can then purify it. In a nutshell.
And then the next step after that
is the characterization. That's when we start doing all the analytics in the laboratory, running the gels, making sure it's pure and of the right size, running the SEC to ensure that it's monodisperse, running what we call a non-specific ELISA, which is really a proxy for pharmacokinetics, for ensuring that when we put that molecule in vivo, that it will behave reasonably well. Those are the basic tests that we do, and then we also have a series of cell-based analyses that we can do to determine what the function of the antibody is, which is really the drug-treating properties of the antibodies, the function. Does it block what we think it does? Does it activate what we think it does? Does it behave the way we think it does? For instance, a lot of what we do is in oncology, so does it shrink a tumor when you put it in a mouse? If there's a mouse with a tumor, can you shrink that tumor by treating it with this antibody and essentially invoking and soliciting and co-opting the function of the immune system against that tumor? So it's kind of there's dual function. Antibodies are multifunctional. They've got different regions of the antibody that have different functions. Only one of which is encoded by what we engineer and design.
We have a pretty specific idea of what they're going to target. And this is, again, comes down to the understanding of what we call structure function and sequence function, is that the binding of an antibody to a target is exactly encoded in both in the CDRs of the antibody. So these binding loops, the sequence of those loops, the primary amino acid sequence of those loops will determine its specificity and affinity and biophysical properties for a particular target.